everyone. In this lecture we'll be seeing certain problems based on continuous time Fourier transform. So the first question is, find the Fourier transform of x of t is equal to cos omega 0 t, and we know Euler's formula, that is cos omega 0 t, can be expressed in terms of exponentials as e raised to j omega 0 t plus e raised to minus j omega 0 t divided by 2, and therefore this can be written as the 1 by 2 times the Fourier transform of the term e raised to j omega 0 t plus Fourier transform of e raised to minus j omega 0 t. Also, we have seen earlier that the Fourier transform of the term e raised to j omega 0 t is 2 pi into delta of omega minus omega 0, and Fourier of e raised to minus j omega 0 t is 2 pi into delta of omega plus omega 0. Therefore, that is substituted here, and this 2 and 2 in the denominator and 2 in the numerator cancels. Therefore, x of omega Fourier transform is pi into delta of omega minus omega 0 plus delta of omega plus omega 0. That is, if we observe, it is clear that the Fourier transform consists of two impulses which are located at omega equal to omega 0 and omega equal to minus omega 0. Therefore, the CTFT of cos omega 0 t consists of two impulses which are located at minus omega 0 and plus omega 0, and whose amplitude is pi. Okay. Next is, find the Fourier transform of x of t is equal to sine omega 0 t, and again sine can be expressed as sine omega 0 t is equal to e raised to j omega 0 t minus e raised to minus j omega 0 t whole divided by 2j. Okay. Again, so the Fourier transform x of omega is 1 by 2j into, within bracket, 2 pi into Fourier of e raised to j omega 0 t is del 2 pi into delta of omega minus omega 0 minus 2 pi into delta of omega plus omega 0. Therefore, we have obtained it as pi by j into delta of omega minus omega 0 minus delta of omega plus omega 0. Okay. Again, two impulses. Next question, find the Fourier transform of the signum function, that is x of t is equal to signum of t, and the signum function is defined like this. It is having a value for t greater than 0 and having a value minus 1 for t less than 0, and it is 0 at t equal to 0. Now this signum function can be expressed in terms of the unit step in this manner. It is equal to u of t minus u of minus t. U of t is extending from 0 to infinity having a value 1, and u of minus t is extending from minus 0 to minus infinity having a value 1. So this minus here accounts for this minus 1. Okay. Next is, so this signal unit step function, it is not absolutely integrable. Therefore, we approach this problem by considering this signum to be the sum of exponentials, that is e raised to minus at ut minus e raised to at into u of minus t, and the limit is, we are taking that a value is tending to 0. Okay. So that is the signum function is expressed here, x of t, it is 1 for t greater than 0 minus 1 for t less than 0, and this e raised to minus at u of t, it is a decaying exponential. Here it is from minus infinity to 0, e raised to at u of minus t minus e raised to at u of minus t. Okay. Then next is, therefore the signum function can be expressed as limit a tending to 0, e raised to minus at into u of t minus e raised to at into u of minus t. Okay. Now we are taking its Fourier transform x of omega, and it is limit a tending to 0 Fourier of the terms within the bracket. Now what is Fourier of e raised to minus at into u of t? That we have already derived and got as 1 by a plus j omega minus Fourier of e raised to at into u of minus t is nothing but 1 by a minus j omega. So when we combine the two terms, that is by taking the LCM is going to be a square plus omega square, that is a product of these two complex terms, and we get it as limit a tending to 0 minus 2j omega divided by a square plus omega square. So when we put a as 0, we get in this form, and it is 2 divided by j omega. Therefore we can say the Fourier transform CTFT of the signum function is 2 by j omega, and we can see that this is a complex number. So the magnitude of this is 2 by omega, and the phase angle is minus pi by 2, that is phase angle is minus tan inverse omega by 0, and it is minus pi by 2 when omega greater than 0, and it is pi by 2 when omega less than 0. Okay, so here we have the signum function. This is its magnitude, and this is representing the phase angle. Okay, next is the question is to find the Fourier transform of the unit step function u of t, and we can do it mainly using two methods. We'll see the explanation for the first method, and this unit step function can be expressed in terms of signum function. So it can be written as a 2 into u of t, that is equal to 1 plus signum of t. So when we add 1 to the signum function, all the negative value, that is the value less than 0, for t less than 0 becomes 0, and for t greater than 0 it becomes 1 plus 1, 2. So that is equal to 2 into u of t. Therefore u of t is taking this 2 to the left side, 1 by 2 plus 1 by 2 into signum of t, and we can find the Fourier transform of u of t. That is, it is expressed as the sum of a constant plus the signum function, and it is so the Fourier of 1 by 2 plus 1 by 2 into signum of t. And what is the Fourier of 1 by 2? It is 2 pi into delta of omega. Also the Fourier of signum of t is 1 by 2 into Fourier of signum of t is 2 by j omega. Therefore u of omega is pi into delta of omega plus 1 by j omega. Okay, now this is second method, that is again by taking the exponential term e raised to minus at ut, applying the limits and integrating, and you will get the same answer. Okay, thank you.